kok sudah online? Waduh. Alright, pencet barusan. Jadi, so before we started, I would like to say something to my usual Indonesian audience. So, saudara-saudara para penonton bahasa Indonesia, jadi mungkin saya mau menjelaskan dalam bahasa Inggris, bukan sok-sokan, dan saya juga nggak jago bahasa Inggrisnya juga. Ya. Kenapa bahasa Inggris? Karena materinya mungkin sedikit di luar materi yang biasanya dikonsumsi oleh kebanyakan viewer saya, ya. Jadi begitu. Okay, so let's get started. So as you have seen that I found some problem from Twitter this morning, which is about polynomial with real zeros. Let me do something. Sorry. Let me show you the real post. What is it? Oh, I think I couldn't find it anymore. Okay, just rewrite. So the problem is as followed. So let p of x be polynomial where all the roots are real. Show that p prime of x squared is greater or equal to p of x p double prime of x. Okay, so here is the problem. So when I look at this problem and rewrite this inequality as follows. This reminds me of a kind of product rule in taking the derivative. Remember that if you have like the derivative of f of x times g of x, right? It's equal to f prime of x, g of x plus f of x, g prime of x, where you take turn taking derivatives. So here also, if we put, for example, p prime of x and p of x, or p of x and p prime of x, this, then you will have take the derivative of the first one, so it's gonna be p prime of x squared, but this is a plus now, p of x, p double prime of x. So it is similar but not quite, right? So then we remember that something similar to the product rule is of course the quotient rule, right? So if we do instead the, let's say, we want to have something like this, right? P of x divided by p prime of x. Take the derivative of that. It's gonna be p prime of x squared minus p of x p prime of p double prime of x divided by p prime of x squared. This is interesting. I didn't see this. Really, this is right. Oh, okay. Now, so basically, if what we want is that we wanted the numerator to be greater or equal to 0. So in some sense, it is equivalent to say that the graph of p of x over p prime of x is increasing, right? But then I abandoned the idea, this idea, to find the relationship between this expression and between this expression and the thing that we are looking for. But we will come back to this equation later. So then, after this failed attempt, I asked myself that, what if we do some induction? Will it work? So let's try induction, right? So this is what, if we look at the first glance, perhaps induction is not the first method that comes to our mind, but as you may see, that induction is quite powerful, that you can use it in many occasions. So okay, let's try. If p of x is a constant, then p prime of x is gonna be 0, right? And also p double prime of x is gonna be 0. So because of that, then clearly p prime of x is equal to, p prime of x squared is equal to p of x times p double prime of x, because both sides are equal to 0, which means that the inequality still hold true, right? This statement is true. Okay, so it works for a constant. Then we can try to see some pattern. What happens if it is a polynomial of that has one root? Let's say x minus a, for example, whatever, like this. This is just some some experimentation, right? P prime of x is equal to alpha, and then p double prime of x is equal to 0. From this, of course, lambda squared is bigger than equal to 0, hence is the same thing as p prime of x squared is greater or equal to px, p double prime x. Right. So this statement check for polynomial of degree 1, right? So now it seems induction might work. Okay, so suppose it is true for all polynomials p of x of degree less than n, right? Of course, this p of x need to satisfy the condition of the problem, which is all its root are real numbers. Okay, so now we look at in the case where p of x is of degree n. So let p of x be equal to, let's say, alpha x minus x1, x minus x2, blah blah blah, x minus xn, right? Or better, because we don't want to specify like this, let me write it in this way: q of x times x minus a, for example, right? Since all the roots are real, we can rewrite p of x as x minus a times polynomial of degree less than n, right? So where degree of qx is less than n. So we are hoping of using induction on the polynomial q later, if we are needed. Okay, let's compute p prime of x using the multiplication rule, which is k prime. Okay, I will just drop the parentheses with x in it. Just write down as q prime, which means q prime of x minus a, and then keep the q, and then take the derivative of x minus a, which is 1, and then take the derivative one more time, q double prime x minus a. So take the derivative of the first term, q prime times 1. I think I made something. Okay, and then take the derivative of this, which is q prime. So this is equal to q double prime x minus a, and then this is twice of q prime. And we would like to compare between the value of p prime of x squared and p of x times p double prime of x. So if you compute p prime of x squared, just square this guy. So we will have q prime squared x minus a squared plus q squared plus twice of this, plus twice q prime x minus a. That's our p prime of x. Now what do we have if we multiply p of x and p double prime of x? Remember that p of x is q times x minus a. So we will multiply this guy with this guy. Okay, multiply this with the first term, we will have q double prime, and there are two x minus a. It's gonna be x minus a squared, and then we multiply this guy with this guy, plus 2q prime x minus a. Okay, so if we compare these two expressions, they are similar, right? The only difference is this factor. Wow, sorry, it's not really similar. We need to use the induction hypothesis. Remember that according to the induction hypothesis, that the statement is true for all polynomial of degree less than n. Here, the q satisfying the hypothesis, so it means q prime square is bigger, or yes, bigger, greater or equal to q times q double prime, right? And we need that when we compare this and that. Okay, so this says that this term is greater than that term. Okay, and this one are equal. So therefore, because this is bigger than that, these are equal, and this is greater than 0, therefore this guy will be bigger than that one. Right? So we are done. Okay. Yeah. So maybe I just write this. Since A greater or equal to B by induction hypothesis, then p prime of x squared is greater or equal to p of x p double prime of x. And we are done. QED. Okay, so now let's go back to the original idea. So after I done with the induction, I look at how other people answer this question. That's how we learn math, actually. So we do some look back according to the Polynomial terminology. So when you are done solving a problem, you sit and then you think over how to solve this problem in a better way. Is there any other thing that we overlook or something like that? Okay. So instead of looking p of x divided by p prime of x, I should be looking at this expression instead. Why? Because this expression is more familiar to us, especially to the calculus student that we the first semester calculus student. Remember that when we have something like this, for example, and we want to find the derivative of y, so what we do is take the derivative of this 1 over y times y prime is equal to the derivative of this. So in particular, here on the left hand side we have that kind of expression, the derivative divided by the function. So this p prime of x divided by p of x is more beneficial, right? But actually at the beginning I was thinking that perhaps it has something to do with logarithm, the natural log function, but we don't really need it, even though we may using it, but we don't really need it. So instead, just write down okay, so this is method number 2, which is probably more direct than the induction. So write down p of x as the product of this from 1 to n, for example, and you need to remember the generalization of the product rule. So for example, if you have, let's say, a product of 3 functions like this, how we take the derivative of this? We take turn taking the derivative of each of these functions. So it could be f prime gh. So first we take the derivative of the first function and keep the rest, and then next time take the derivative of the second function and keep the rest, and next time take the derivative of the third function and keep the rest, something like that. So then in this case, if we have our p of x is written in this form, then p prime of x will be by using, remember this big pi is a symbol for products. Yeah. So it is a product of x minus xi, where I runs from 1 up to n. So then the derivative will be, so we have this kind of expression, similar, the product of this, but we take the derivative of one of them. When we take the derivative of this one expression, then we know that the answer is 1, right? Maybe I'm just, okay, this is not really, is it really the general, is this a general form of all polynomials with real roots? Can we have something like, yeah, I think maybe we can like this. Yes, this okay. Okay, so what I mean is, okay, so we still have this kind of expression but missing one of them. So maybe as an illustration, for example, I have x minus a times x minus b times x minus c. If we take the derivative of this, then when we take the derivative of this, it is 1. So it's gonna be x minus b, x minus c, and then the next one is minus a, x minus c, and the next one gonna be x minus a, x minus b. Okay, so it is product but with less terms, right? So what we do actually is a product of this kind of expression but missing one of them. Let's say I is not equal to j. And we sum it, j from 1 to n. That's the derivative of p prime of x. Okay, now if we do p prime of x divided by p of x, then this alpha cancel. So what we have is the sigma, the product from 1 to n, where I is equal, where I is not equal to j. So here there is a restriction that I is not equal to j, but on the bottom there is no restriction. We divide this by p of x. So this is a product from 1 up to n of x minus xi. Okay. So if we simplify this expression, they are similar. The only difference is that on the numerator we don't have x minus xj. Meanwhile, on the bottom we have x minus xj. So therefore, if we simplify this, this is going to be 1 over x minus xj, where j runs from 1 up to n. Right. Okay. So now we know how to obtain this kind of expression before, right? This kind of expression, which is when we take the derivative of the expression. Okay, let's do it. Take the derivative of this guy, d dx of p prime of x is equal to no, I want to do, yes, oh, it's going to be the opposite, the other way around. P double prime of x times p of x minus p prime of x times p prime of x divided by p of x squared. Okay, so this is the derivative of the left hand side, and the derivative of the right hand side of this is the sum. So think of this as x minus xj to the power of -1. So it's going to be negative x minus xj to -2. Okay, or just to make it more transparent, this is negative 1 over x minus xj squared. Or if you would like, we can also move the negative sign in front of the sigma to make it clear then that this is a non-positive number, right? Because this is a square and we add so remember that the square is never a negative number. Sorry, yeah, okay. But if we put negative sign, then it is suddenly this guy is less or equal to 0. Okay, so it means that this expression is also less or equal to 0, but the denominator is never negative. So therefore, the numerator must be negative. So comparing with that, so maybe I will not write down word by word, just using verbal explanation, that since this is less or equal to 0, it implies that the expression on the top, on the numerator, must be negative as well. So we have this then. And this is exactly what we wanted to prove. Okay. Yes, I think that's good enough for daily math today. So if I came across some problem on the internet, we will discuss it. Okay, thank you for watching. See you again on the next.